Welcome back to ECE 320A. In this Unit 5 video, we are going to be looking at going from a YY balanced three-phase circuit into or extracting from that a single-phase equivalent circuit. That's material in Chapter 11, and again, at the end of Unit 5, you will have exam number 2. Let's just remind ourselves of the notation that we are using. We're using a double subscripted notation, and if I now say V sub AB, that's meaning the voltage drop from the first subscript, which in this case is A, to the second subscript, which in this case is B. So if I had two terminals, A and B, and I say V sub AB, then I'm interested in the voltage dropped from terminal A to terminal B, or if I had a multimeter, I would take the negative lead and set it on B, the positive lead and set it on terminal A, and measure that potential difference between terminals A and B. What we want to do now is actually find a single-phase equivalent circuit from a balanced three-phase YY circuit, and one of the key words in that title is balanced. We need to make sure that the three-phase circuit is balanced, and once it is, then we can remove just one phase of that, analyze that, which is now a simple mesh circuit, and from that produce the complex power of the load, the complex power in the transmission lines, and if we need to expand that to the total system, we would then just scale everything by 3 when we're looking at all three phases. Let's just go ahead and give you the punchline of what we're doing. We're wanting to begin, or we're beginning with a three-phase balanced YY circuit. All of these similarly subscripted Z's are equal to each other, so the A, B, and C's are equal. And I've also introduced a neutral conductor, which in this case could have an impedance Z sub 0 in that neutral conductor. And I've tried to label the different currents and voltages. You can see that the A phase voltage at the load, V sub capital AN, over here, is labeled from terminal A down to the neutral conductor. We do have a neutral conductor in our circuit, and we could associate with that a voltage drop from the capital N terminal to the reference terminal little n. So the reference terminal little n is what we would sort of say is our 0 point or our ground, and we would have every measurement relative to that if we were measuring voltages with a multimeter. And if we want, we can identify our line current in the A phase, which in this case is also our A phase load current, but the line-to-line voltage at the terminals, the load terminals, that is V sub AB, and that's not the same as the A phase voltage, which is V sub AN. But we want to now, here's the punchline, we want to extract from this a single-phase equivalent circuit, which looks like this. And you can see that we have all of the pieces. We have our generator voltage, we have our generator impedance, Z sub lowercase GA, we have our transmission line in the A phase, and we have our load impedance in the A phase, and we also have a neutral conductor with no impedance from capital N to little n, those terminals. And what we want to do now is the analysis that will take us from this balanced three-phase YY circuit to this single phase equivalent. And to get us started, what we want to do is look at finding or determining the current I sub 0 in this neutral conductor. We're now wanting to find that particular current. How do we do that? What would be a quiz, or what question would you need to answer in order to find I naught? Well, the quiz that I could ask you, or could have asked you, would be to write Kirchhoff's current law, or a KCL equation, at node little n, where node little n is the reference node, and that's now right there, that I've now dashed, encircled on the left middle of the YY configuration. And can you now mentally write a KCL equation at that particular node? All you're doing is you have 4 wires going into that node. You just want to algebraically sum up all of the currents that you have entering or leaving. So again, it's algebraically correct. What is making up the currents in and out of that reference node little n? I hope you can see that you have I sub 0 that I've highlighted in light blue. We also have all of the line currents, I sub AA, I sub BB, and I sub CC. Putting this diagram in memory for just a little bit, I hope you see that I sub 0 is going into node N, and all of the line currents, or phase currents in this case, are leaving little n. Algebraically then, if we wrote the KCL equation at little n, we would see that I sub 0, the current going into that node, is equal to the sum of the currents leaving that node. That's KCL at n, and that would be the answer to that equation if you didn't need to go any further. But now let's write that in terms of values that we might have available to us. Maybe we now have all of these generator voltages. Maybe we also have this voltage V sub n at that node. If that's the case, and we know all of these impedances in the various branches or phases of this three-phase circuit, I hope you can see that we can now write an equation for I sub 0. I sub 0, just use Ohm's law, generalized form. We have I sub 0 is just V sub capital N divided by the impedance in that neutral conductor, which is Z sub 0. That's I sub 0. So I sub 0 is then V sub n over Z sub 0. And that's equal to I sub AA. I sub AA is going from left to right. What's driving that is V sub A prime n, and that voltage from that generator in the A phase is dropped across all 3 of those impedances in the A phase line, Z sub GA, Z sub LA, and Z sub A. And the voltage dropped across those is not quite just V sub A prime n, it's actually V sub A prime n minus V sub capital N. That's the voltage dropped across those 3 impedances. Or I sub AA is now V sub A prime n minus V sub n. That's the voltage dropped across those impedances, and those impedances are summed down below to give us the total impedance in that branch, and that's now the current I sub AA. I sub BB, I hope you can see we have a balanced three-phase system. Structurally, it's the same as what we just computed, except now we have the B subscripts, and likewise for I sub CC. Or I sub BB is now V sub B prime N minus V sub N over, and now just to minimize the writing, and we're assuming that this is balanced, that's now the same as Z sub GB plus Z sub LB plus Z sub B. And finally, then we have our I sub CC, which is V sub C prime N minus V sub N over Z sub phi. We said one of the key words in this entire process of going from three-phase to single-phase equivalent was that our three-phase system was balanced. And what do we mean by that? Let's now just define some of the conditions that are valid when we have a balanced three-phase circuit. A three-phase circuit is balanced if we have the following conditions that are true. One is that VA prime N, that phasor, V sub B prime N, and V sub C prime N, those three generator voltages form a set of balanced three-phase voltages. By that, I mean that V sub A prime N plus V sub B prime N plus V sub C prime N, they all have the same magnitude. They, depending on the phase sequence, whether it's positive or negative, are 120 degrees away from each other. And when you add those up, remember to draw the vectors, and they end up coming right back where you started as a combination. So those three phasors add to 0. And we want a balanced set of three-phase voltages at our source or at the generators. We also want all the impedances to be the same. We have our generator impedances in the different phases, in the three phases. We want those to be equal. For a balanced three-phase system. We also want our transmission line impedances to be equal. And finally, in a balanced three-phase system, we are assuming that the load impedances of all three phases are equal. Under those conditions, then we can actually find or we can prove or verify the following fact. If the system is balanced, then we can actually show that that voltage at the capital N terminal between capital N and little n, that voltage is actually 0. So let's show that or verify or prove that particular fact. And to simplify, let's just say that Z sub phi is the sum of the three impedances in one of the phases. Here, let's just say it's the A phase. Then we can write that KCL equation right here. We're starting with that. Hopefully you believe that that equation is valid. Now let's pull all of the V sub capital N's to the left-hand side of the equality and leave the generator voltages, the primes, those terms on the right-hand side. And again, everything is going to be over something like a Z sub phi, although we still have this Z sub 0 over on the left. But hopefully you can see that we're going to end up with 3 V sub capital N's adding to this V sub n over I sub z over Z sub 0 on the left. So from our KCL equation, we can say that V sub n times 1 over Z sub 0 plus 3 over Z sub phi, that's equal to, and again, what we had over on the right-hand side was V sub a prime added to V sub b prime plus V sub c prime. All of those had the same denominator, but now what did we say if we have a balanced three-phase system? We said that those sum to 0. We're assuming that we have some non-zero impedance going on. So in fact, this on the right is 0. We're dividing by a non-zero term, so that's okay. We have 0 on the right. Here, this is not equal to 0, so that means that we have some non-zero quantity times V sub n equaling 0. Well, if the product of that expression on the left has to equal 0, then the only way that that can happen, since the one term in that product is not equal to 0, that now allows us to conclude that V sub n, capital V sub n, is equal to 0. What does that mean here? Now we know our reference node was little n, and that was 0. Now we know capital N is 0. That means there's no voltage drop across that neutral conductor. So let's see what we can conclude from this fact that V sub n is equal to 0, V sub capital N. There is no voltage between the source, neutral, which we were calling little n, and the load neutral, which we've been labeling as capital N. And from that, we can then say if there's no voltage dropped across that neutral conductor, then we have nothing that would push current through that neutral conductor. So we have a star which says that there's no voltage between the neutral source and the load neutral, and that then allows us to conclude that there's no current that's flowing in that neutral conductor. There's no voltage drop, which means that there's no current flowing. Those two stars actually give us two different options, or lead to two different ways of working with what we're now given. One, we could remove the neutral conductor. Since there's nothing going on in that neutral conductor, we could just take it out of our circuit, because there's no current flowing. Or we could replace the neutral conductor with a bare wire. Since the voltage at little n is the same as the voltage at capital N, we can ensure that by shorting those two terminals together. So we could replace the neutral conductor with a perfect short circuit. And now we can do a little bit more analysis. What if we wanted to look at the currents that we have? Suppose we now look at I sub AA, the transmission line current, or the A phase line current. That was now V sub A prime N minus V sub N over Z sub phi. But now if V sub capital N is 0, we might as well just write that as V sub A prime N over Z phi. Similarly, we could write I sub BB. That's now V sub B prime of N minus V sub N over Z sub phi. But again, V sub capital N is 0, so why bother? And I sub CC is now V sub C prime N over Z sub phi. And now what does that show us? Well, remember how these generator voltages are related. V sub A prime N, V sub B prime N, and V sub C prime N formed a balanced set of voltages, which meant they had the same amplitude and their phases were all related by 120 degrees. So in this case, the denominator on the right-hand side of all of those current expressions is the same. It may be a complex number, but it's doing the same thing to every one of those right-hand sides. So that means that these currents actually form themselves a balanced set of three-phase currents. Therefore, the currents have the same magnitude. So therefore, the current in each line is equal in amplitude and frequency and those three are 120 degrees apart, each of those three current phasors, and are 120 degrees out of phase with each other. And that now allows us actually to write down or to sketch this single phase equivalent that we had already alluded to in our punchline. If we now want to analyze that three-phase YY balanced system, we could just as easily analyze that system by analyzing a single phase, and it might as well be the A phase, because now we know that all of the generator voltages are related by 120 degrees. They have the same magnitude, and we've just shown that each of the currents in the three different phases form a balanced set. So if I can now find I sub AA, then I know what I sub BB is and I sub CC is. Obviously, I'll need to know what the phase sequence is. Is it a positive phase sequence or is it a negative phase sequence? But once I know that, then I know that I have determined, once I've determined one of these, I can just find the other two quite easily. And here, let me just call this connection between capital N and lowercase n. This is the neutral conductor. With no impedance in the single phase equivalent. And what we have to maybe keep in mind, it typically won't hopefully hurt us too much, but we have to realize that if we now looked at the current in the neutral conductor in this single phase equivalent, that's I sub AA. But in the three-phase circuit, the current in the neutral conductor is a combination of I sub AA, I sub BB, and I sub CC. And you can see that either by writing KCL at little n or writing KCL at capital N. I want to just then make that clear. Note that if we look at the A phase current in the equivalent circuit, I sub AA, and if we computed that, and that would not be a difficult computation because we simply have a single mesh current analysis to perform. That I sub AA is in fact equal to the I sub AA in the balanced three-phase circuit. But what we can't do is we can't move beyond that. I sub AA, if we now look at I sub AA as flowing here, in the single phase equivalent, we will have I sub AA in that neutral conductor in the equivalent circuit. But if we now move back into the three-phase circuit, we don't just have I sub AA flowing in the neutral conductor. We have I sub AA, I sub BB, and I sub CC. And that's what I want to try to make clear. I sub AA, the current in the neutral conductor, in the equivalent circuit that indeed is not equal to the current in the neutral conductor of the balanced three-phase circuit. Because we know that the current in the balanced three-phase circuit neutral conductor is I sub 0, and that by KCL, we've already written that down, and we use that to show many of the different relationships to derive that single phase equivalent. This is the actual neutral conductor current in the three-phase balanced system. And I think from that particular equation, it's clear that that's not equal to I sub AA. And what we want to do now is start reminding ourselves or making the connection between the different voltages and currents depending on the wiring or connections in either the sources or the loads. We now should be very comfortable with understanding what we're talking about when we refer to phase voltages and phase currents and line voltages and line currents. And we'll pick up at that point in subsequent lectures.